Energy is everywhere. It moves, transforms, flows through every process, and yet no one has ever seen it. You cannot touch energy. You cannot isolate it as an object. You only see what it does. A moving car, a glowing filament, a falling stone. We say energy is there, but what is actually there? We assume energy is a kind of substance, something carried by objects, stored, transferred, used up, like fuel. But this intuition is wrong. Energy is not a thing, and yet it is one of the most precisely defined quantities in physics and one of the most strictly conserved. Always the same total, never created, never destroyed. Why? Why should the universe obey such a rule, and what exactly is being conserved? To understand this, we begin with intuition. In everyday life, energy feels concrete. Food gives you energy, batteries store energy, fuel releases energy. We imagine it as something contained, a hidden reservoir inside objects. When you lift a weight, you put energy into it. When it falls, it gives energy back. This language is useful, but it hides something deeper. Because in physics, energy is not defined as a substance. It is defined as a number, a value assigned to a system, a measure of its capacity to change. Kinetic energy depends on motion. Potential energy depends on configuration. Thermal energy depends on microscopic activity. Different forms, same concept. But here is the first shift. These forms are not separate things. They are different ways of describing the same accounting system. Energy is not what flows. It is what remains consistent when everything else changes. This becomes clearer in classical mechanics. A moving object has kinetic energy. If it slows down, that energy does not disappear. It transfers to heat, to sound, to deformation. Track all contributions, and the total remains constant. This is not an assumption. It is an empirical fact, repeatedly confirmed. But classical physics leaves a question open. Why should this be true? Why should there be a quantity that never changes, no matter what happens? To see where intuition fails, we need to look deeper. Consider a simple system, a pendulum. It swings back and forth. At the top, it stops briefly. At the bottom, it moves fastest. Potential energy converts into kinetic energy, then back again. Nothing mysterious, but now imagine friction, air resistance, internal damping. The motion slows. Eventually, the pendulum stops. Where did the energy go? It did not vanish. It dispersed into microscopic motion, into heat, into the environment. Energy is still conserved, but no longer accessible in the same way. Already, the idea of usable energy becomes distinct from total energy. But conservation still holds, even in complex systems, even in chaotic processes, even when energy spreads beyond recovery. Now step into modern physics. The concept of energy becomes even less intuitive. In relativity, mass itself is energy, not metaphorically, literally. A stationary object contains energy, E equals mc squared. Mass is a form of energy, which means energy is not something objects have. Objects are configurations of energy. But this still does not explain conservation. It only expands the definition. The real answer lies deeper, not in what energy is, but in why it must be conserved. And that takes us into the structure of physical law itself. At first, Conservation looks like a rule, a constraint imposed on nature. But in modern physics, it is something else. It is a consequence of symmetry. This is not interpretation. This is a precise mathematical result. In the early 20th century, Emmy Noether proved a remarkable theorem. If the laws of physics are the same over time, then energy is conserved. This is a fact, not philosophical, not optional. If the rules governing a system do not change from one moment to the next, then there exists a quantity that remains constant. That quantity is energy. This is the key shift. Energy conservation is not about energy itself. It is about time. More precisely, it is about time symmetry. If you perform an experiment today, or tomorrow, or a million years ago, and the underlying laws are identical, then energy must be conserved. If the laws changed over time, energy conservation would break. So what we call energy is the mathematical expression of a deeper invariance, the invariance of physical law under time translation. This reframes everything. Energy is not a substance. It is a bookkeeping quantity that exists because time is uniform. Now consider what this means. We often think of time as something that flows, but physics does not require flow. It requires consistency. The equations must work the same way, regardless of when you apply them. That condition alone forces conservation. And this extends further. Other conservation laws follow similar logic. If space is uniform, momentum is conserved. If space has no preferred direction, angular momentum is conserved. Each symmetry produces a conserved quantity. This is not coincidence, it is structure. The laws of physics are built around symmetries, and conservation laws are their shadows. Now we must be precise. The statement, energy is conserved, means that within a closed system, the total energy remains constant over time. But what counts as a closed system? In practice, perfect isolation is impossible. Energy always leaks, interacts, spreads. But the principle remains valid for any well-defined system. Now consider a deeper layer. In general relativity, the situation becomes more subtle. Space-time itself is dynamic. It curves, expands, evolves, and in certain cases, global energy conservation becomes ambiguous. For example, in an expanding universe, the energy of photons decreases as their wavelength stretches. Where does that energy go? There is no simple answer, because in curved space-time, the definition of total energy is not always globally well-defined. This is not a failure of physics. It is a limitation of applying classical intuition to a dynamic geometry. Locally, conservation still holds. Globally, the concept becomes dependent on how space-time behaves. So even here, we must be careful. Energy conservation is exact, but only within the correct framework. Now return to the central idea. Energy is not a thing. It does not exist independently. It is a property of a system's description. A number that remains constant because the laws of physics do not change over time. Different interpretations may frame this differently. Some treat energy as fundamental, others as derived. But the mathematical structure is unambiguous. Energy conservation follows from time symmetry. This is not a guess, it is a theorem. And this leads to a deeper implication. If the laws of physics were different, if time behaved differently, energy might not exist at all, or it might not be conserved. So, energy is not a universal substance. It is a feature of this universe's structure, a consequence of how its laws are organized. And that changes how we should think about it. We began with a simple intuition. Energy as something real, something stored, something that flows. But physics replaces that picture. Energy is not what moves through the system. It is what stays constant when everything moves. It is not a physical entity. It is a constraint, a consistency condition imposed by symmetry. This is a radical shift, because it means energy is not part of reality in the way objects are. It is part of how reality is described. Now consider the implications. When you watch a process, a collision, a chemical reaction, a star burning, you see change. You see transformation. But beneath that transformation, there is a hidden invariance, a quantity that does not change. That invariance is energy, but it exists only because the laws themselves are stable. If time were not uniform, if the rules evolved moment by moment, there would be no conserved energy. So, energy is not fundamental in isolation. It is relational, defined by the symmetry of time. This connects to a broader pattern. Modern physics increasingly describes reality not as a collection of things, but as a structure of relations and constraints. Energy fits into that pattern. It is not a building block. It is a rule that emerges from deeper structure. Now we must be careful again. This does not make energy unreal. It makes it precise. Energy is measurable, predictive, indispensable. But its meaning is not what intuition suggests. It is not a substance. It is a conserved quantity, defined mathematically, tested experimentally, derived from symmetry. Different interpretations exist. Some frameworks treat energy as more fundamental. Others emphasize symmetry as primary. But all agree on the observable consequences. Energy conservation holds because time symmetry holds. Now step back. We often ask, what is the universe made of? Matter? Energy? Fields? But this question may be incomplete, because energy itself is not made of anything. It is a feature of how the universe behaves, a reflection of its internal consistency. So perhaps the deeper question is not, what is energy, but why does the universe have symmetries at all? Why should the laws remain the same over time? Why should there be invariance? Physics does not yet answer this. It describes the consequences, not the origin. And that leaves us with a final shift. Energy is not a thing you can point to. It is a rule you can rely on. A hidden order beneath change. A constant beneath transformation. Not visible, but always present in the structure. And if that is true, then what we call energy is not part of the furniture of reality. It is part of its logic, a constraint woven into the way the universe allows itself to evolve. And that raises a deeper possibility. Perhaps reality is not defined by what exists, but by what must remain consistent as it changes. And energy is one expression of that necessity.